Dear friends, welcome back. So, in our previous lecture we have solved for weight estimation problem, where the UAV that we have considered has to perform a surveillance mission for 2 hours with carrying a payload of which is electro-optical and IR sensor, which weighs about 1 kg with a flight velocity of 30 meters per second. What we are asked to do is, what will be the total takeoff weight of the system if the flight happens at 15 L/d of 15, right, if the corresponding cruise flight happens at 15 L/d, and then we were also given the data about efficiency, right. So, we have solved this by means of this subroutine, where we have considered the weight and the ratios and the weight ratios from the baseline UAV, which was given from the data like in the question itself. And then what we did is, after considering the efficiency of the propeller, right, various efficiency factors here, then we proceeded to figure out what is the battery weight. For the initial iterations, we considered the baseline weight to start with, and then for this particular mission requirement, what will be the weight of the battery required, thereby updating the total weight of the aircraft, right, and using it to compare or using and finding out the error with respect to the previous weight, right, which the baseline aircraft, right, for the first iteration. So, the previous weight will be the baseline aircraft weight for the first iteration here, and then we compared the error and we checked if it is less than 10 power minus 10, then it will stop, right, the code will stop. So, that means, so from the first iterations, where the so during these first iterations, first while loop here, during this first while loop, what we did is we updated battery weight, right, and the overall weight, but this weight, structural weight and propulsion weight are estimated using weight fractions. Yes, of course, we will keep the weight fraction same for throughout this process, but based upon the initial baseline aircraft weight. Now, the need is to upgrade them to the current aircraft weight. So, what we did is, after this first while loop, right. So, again the structural weight is updated by means of the current weight of the aircraft, which was obtained from the above loop, right, where the battery weight has been updated based upon the current mission requirements, right. So, from there the weight of the propulsion system is also upgraded. Now, the weight, now this structural weight and the propulsion weight corresponds to the current UAV for the current mission requirements, right. So, similar so this weight that was output from this earlier while loop will now become the input for the second while loop, which will again, because of the change in the weights of the structural and propulsion systems. So, the battery weight or the power requirement will also change, as the overall weight has to change. So, the battery weight has to change, right. So, and hence we have iterated it again to figure out what is the updated weight of the aircraft. So, the final weight of the aircraft we obtained after this second while loop for a particular L/d. So, this for loop iterates for different L/d starting from 11 to 16 with the increment of 1, right. So, for each and every L/d we are trying to find out what is the total takeoff or total weight of the aircraft. We are estimating total weight of the aircraft. During the process we also figured out what should be the total battery weight for that particular L/d, what should be the structural weight as well as propulsion weight, and we have plotted that, right. So, from the plot we noticed that from the question so in the question we were asked like what will be the total takeoff weight when we are flying at L/d 15. So, it will be about 8.1 kg. Now, let us consider this as an input and the L/d as an input as well as the flight velocity as an input to figure out what should be the typical planform geometry or planform parameters, or what should be the typical wing planform geometry that helps us to fly this aircraft at the desired velocities as per the mission requirements, right. So, that means we are going to get the planform geometry with the method that we are going to use right now, or the subroutine that we are going to develop. Okay. So, what we are going to do here, let us write down the example. Okay. So, this is another example or subroutine for planform geometry selection. Okay. So, estimate with the Planform geometry of the UAV considered in the previous example to perform the same surveillance mission. The surveillance mission is for 2 hours, right. So, that means, so we will consider the same mission requirements here. So, where the velocity has to be 20 meters per second, sorry 30 meters per second it should be. So, the velocity is 30 meters per second and then the flight time is about 2 hours, right. These are the typical mission requirements that we have considered earlier along with this parameters, right. So, but what do we require right now is the following, we just need, because with all other parameters including structural weight ratio and propulsion weight ratio as well as payload and propulsion weight efficiency factor and then electrical efficiency factor and motor efficiency factor. So, including all this, we have figured out that the aircraft when flying at L/D of 15, it has to weigh about 8.1 kg. So, this is what is required for us to go ahead with the Planform geometry selection, right. So, what exactly the Planform has to do here, let us say. So, I am trying to erase this part. So, apart from 30 meters per second, what we have is L/D of 15 and the total weight of the aircraft is 8.1 kg. These are the things that we are going to take it as an input, right. So, now as we know the UAV when performing this mission. So, the first and foremost thing that we expect is at this particular flight velocity, right, what is the corresponding CL that I need to generate, so that I can like satisfy that lift is equal to weight condition, right. So, I can lift this total, otherwise I can generate a force which can sustain the total weight of the aircraft, right. So, which is half rho v square S CL is equals to W. So, I am flying at a particular velocity, which means the CL, so which is designed, is not it. So, we are going to design the aircraft to fly at that particular flight condition, right. So, the design CL depends upon twice the wing loading times rho v square, right, or v infinity square or v design. So, v design is here how much, 30 meters per second, that is what we have to design it for about. So, CL design is 2 times dW, 2 times W by S upon rho v d square, right. Now, so assuming this particular Planform. So, the Planform here, the Planform parameter that comes into this L is equals to W is area of the wing, is not it, area of the Planform. So, that is the only thing that I require to design in the first place, and then we will see how to, we using that Planform, how can I achieve that particular CL design, that we will look into, like then we have to look into the cross sectional properties of that, is not it. So, the wing here, for example, if you take the top view of this, right, of this UAV. So, if you consider the top view of this UAV, so the wing that you are going to design here, right. So, the Planform here Okay. So, this planform here is responsible for generating the lift, right. This particular when moving at this particular velocity will generate the lift combined with some CL value here, non-dimensional. So, the CL here talks about the cross sectional property, right. So, this talks about like you need to talk about the cross section of the wing there. That means, you need to talk in terms of CL alpha, CL naught, alpha design and alpha at which CL is equals to 0, right. So, this we will handle for the time being. We assume that CL is provided, this CL design is provided given I have certain W by S, right. Okay. So, how to achieve that? So, that means I need to know what should be the S. When I say S, I need to talk about what? The span of the UAV, is not it, span of the wings, or say root chord of the wing CR here. So, this is my CR and CT, am I correct or not? CR, CT, B. So, based upon this I can talk about wing planform area, am I correct or not? So, but it is always better to deal in terms of non-dimensional parameters before actually talking in terms of this dimensional variables like CR, CT and B here, right. So, the non-dimensional parameters for wing planform are aspect ratio, which is B square upon S, right, and taper ratio lambda, or taper TR, taper ratio is lambda, is CT upon CR, right. Now, if I consider, so now the question is, if I know here, if I know S, right, and AR, I will be able to find out what is the span of the UAV for that particular S and aspect ratio, am I correct? So, now once I know what is S, right, S is equals to, once I know B, so what is B by 2 times CR times 1 plus lambda. If I know lambda, if lambda is known, right, or say I can make it a variable as well, right. If lambda is known, I can find out what is CR. CR is 2 times S upon B times 1 plus lambda, right, for a straight tapered wing. So, when there is sweep back, sweep and all, right, then you consider the cause of leading edge sweep or any of the leading edge sweep. So, that I am not going to talk about here. So, I am talking about a straight tapered wing here. And then CR, and what about, so I know B, I know CR, right. Once lambda is known, I can also find out CT. CT is equals to CR times lambda. Okay. So, that means I know what is CT, what is CR, what is B. These are good enough parameters to talk about planform area, right. So, this is what we are going to find out. So, what we are going to take as an input is the weight of the UAV that we have estimated and the LYD which we are flying, is not it. So, and what is the velocity of flight. So, these 3 are the parameters that we are going to take it in for this particular algorithm, right. So, what am I doing right now? So, let us write a new script. So, I am not going to write down the detail like steps there, I do not think that is necessary. So, and then altitude. So, you need to know what is the altitude of flight as well. Let us assume it is at 3 kilometers, surveillance mission at, so what was the earlier question, surveillance mission is at, so it was not mentioned there. So, let us consider this is happening at surveillance at 2 kilometers altitude, 2000 meters, 2000 meters. Okay. So, that means we have to use the density function that we have developed earlier, right. So, let us now start the new algorithm, new subroutine. So, what I am going to have here is first enter the altitude, right, is not it, input I am taking the inputs in the first place, enter the altitude of flight in meters. Okay. And then V is, so cruise input, enter the cruise velocity or design velocity. right. Enter the design velocity or desired velocity of flight from the mission requirements, right. Velocity of flight. See, we may not be able to generalize the design process. So, this based upon the mission requirements, you have to figure out which kind of subroutine you have to develop, right, with the respective variables. Since we have velocity as an input here, so I am considering it as a desired velocity here, right. So, the surveillance has to happen at a particular velocity. So, W from the weight estimation algorithm, right. So, let us say this small w, I am considering it as an input, enter the weight of the estimated weight of the aircraft, estimated weight of the UAV, otherwise, okay, in kg. So, this is multiplied by g will give me, right, 9.81 will help me to find out weight in newtons, otherwise capital W is like small w times 9.81 meter per second square. So, I have Z, V, W and capital W, right. Now, so what is design CL? So, for me to find out, so L by D is also an input, but it is rarely used here other than finding CD naught and K, we will use them, we will use those parameters anyways. So, I need to find out what is CL design, right, CL underscore design, CLD underscore D is 2 times of W upon S, isn't it, otherwise W underscore S upon den, right. So, I need to find out the density, den is equals to density of Z, right. So, this will help me to find out what is the density at that particular altitude. So, Z is the altitude that we are considering, altitude of flight that we are considering. So, DENSITY is the function name. So, I am calling that function. So, this is like 2 star W underscore S is wing loading, let us say. So, wing loading upon density times V square, right. Okay. So, that means we understood that, okay, for a given flight velocity at a given altitude. So, if the wing load is varies, the CL design varies, right. That means, so wing loading we consider it as a variable of this iteration, right. So, it varies CD of I comma j, that means, so I stands for the current iteration, which means wing loading W underscore S for W underscore S varying from, say wing loading is varying from 4 to 10, let us say, okay, with an interval of 1. Okay. So, before this what I would like to do is I is equals to 0. So, inside this loop I is a variable of this iteration, which is increasing by 1 for every iteration. So, this is 2 W by S upon rho V square CL design, right. So, what is J here? We have so there is also a variable J, we will try to get back to that soon, otherwise I will use it when we define that, right. So, this is I. So, I comma 1 will return me a column vector. So, I prefer to use column vectors here, and then CL design is now varying with W by S. So, for each and every W by S there is CL design, right. So, how can I find S from here? Yes, or so that means for each and every W by S there is there is ns, am I correct or not, where w by s is a variable here. So, w underscore s is wing loading in Newton per meter square. Okay. So, CL design is CL design. So, wing area based upon input weight and wing loading, right. So, W upon W by S will return me S in meter square here. Okay. So, once I have S, I will be able to find out B, am I correct? B of I comma 1 is equals to, so square root of aspect ratio times S of I comma 1, right. So, now it is a tricky part, is not it? We do not know what is aspect ratio here, right. So, let us now iterate aspect ratio also for different aspect ratio SQRT, yes. So, let us now make it a variable aspect ratio. So, let AR is varying from say 4 to 10, again the same, let us assume. So, with the increment of 1, right. So, W, okay. So, let me call this as small ws, which is in kg per meter square. Okay. So, I am converting this kg per meter square multiplied by 9.81, so that it becomes in Newton per meter square. Okay. So, this ws, let us say capital Ws itself, right. So, is in kg per meter square, when multiplied by 9.81, what I am going to get is Newton per Newton per meter square. So, W here is in newtons. So, W by S is in kgs. So, either I use small w here, so that it is in kg, right. So, it returns in kg per meter square. So, B, for B I need to have aspect ratio as an input. So, aspect ratio is varying here. So, I will use this another variable of this outer loop, right, what is j. So, here j is increasing for every aspect ratio, increment in aspect ratio. So, a value of j corresponds to a particular aspect ratio here. Okay. So, I would like to store this. So, small AR, let us say, of aspect ratio or A underscore R, otherwise aspect ratio, I am storing it just for storing purpose. So, is j comma 1 is equals to AR. Okay. So, now aspect ratio is an input, S is an input to find out what is B based upon wing loading and the initial weight. So, we figured out what is S here, right. So, if you want me to change this as small w underscore, so that will make more sense. Small w is in kg, right, kg multiplied by 9.81 will be newtons, right. So, once we have span of the UAV, we can find out root chord, right, span and area and aspect ratio, say. So, the root chord, in order to find root chord, what we require is lambda as an input, Trapper ratio, right. So, this is 2 times of S of I comma 1 upon. So, here if you see the span, neither span or the area is affected by this taper ratio here, right, is not it. So, that is why it majorly plays between root chord and tip chord, that is how I prefer using it, right. So, that is so the CR here is 2s upon B times B of I, again it is a variable here inside, B of I comma j. So, now whatever I here should be replaced by j for a particular aspect ratio, right. So, all these calculations are for particular aspect ratio. the inner loop runs for a particular AR, that is runs for a particular j value here. Right. So, the I progression here happens with j input. If I want to save this wing, what I can do is capital W underscore S, right. This is just for storage purpose. So, of I comma j, okay. Wing loading. So, wing loading will be again will be same for, right, is not it, similar to that of what we witnessed in our previous subroutines. So, for every j, the column vector of W comma S will remain same, right, because we are varying it, right, we are forcing it to vary with this like from 4 to 10 with an increment of 1. So, this is equals to W underscore S. So, I am using this wing loading for a particular j, and this keeps increasing from 4 to 10, right. So, to calculate CL design and then S span root chord. So, root chord requires an input here, right, lambda is an input here, 1 plus lambda, 2s upon b times 1 plus lambda. So, lambda is taper ratio, let us say lambda is 1 plus TR taper ratio. Okay. So, I am not considering taking in another iteration like another loop here for taper ratio. Instead, you can do that, but instead I would like to do it here for a particular taper ratio, let it be 0.4. Okay. So, either you can consider this as an input, you can make it as an input here instead of W, because W is already done earlier. So, velocity of flight is also more or less known. Let me make this also an input here. So, taper ratio TR is enter the taper ratio of UAV. So, we made this also as an input. So, I get taper ratio from there and it remains constant for this entire iteration, right. So, you can plot multiple, like for various aspect ratio you get for different W by S, you will get to know what is the corresponding like root chord, tip chord and the span and the wing area to generate the desired CL, right. So, based upon this data you find out what is, like now you change the taper ratio, right, you change the input and find out the same plot, so that you have you can also cross plot them to compare or to figure out which taper ratio is more feasible for you to manufacture, right. So, S upon and also we have discussed in length about what is the significance of taper ratio and how it will help for the aerodynamic loading as well, right. So, we have discussed in our previous course. So, you can refer to those lectures. 2s upon b times 1 plus lambda. Okay. So, this makes sense. So, I will just write it down. Wingspan based on AR and aspect ratio and wing area, right. Okay. And then root chord wing CR or root chord based on aspect ratio or say B span and taper ratio. Okay. So, what is CT? Straightforward. CT is CR times lambda, isn't it? CR of I comma j times taper ratio. Taper ratio is an input again here. So, can we find out? So, L by D in the earlier case is what? CL underscore CD is 15 here, that is an input. So, we can also find out what is CD for this L by D, right. CD underscore, let us assume D, right, design of I comma j is equals to CL underscore d of I comma j, which is varying with wing loading, right. So, upon CL by CD, right, CL underscore CD, so which is constant, right. And then we can find out what is K, right, Oswald's efficiency factor K. So, first let us, we have to find out E to figure out what is K. So, E again can be figured out from this empirical relationship. Value of E can be estimated using this empirical relationship based upon the aspect ratio of the wing, 1.78 times 1 minus 0.045 aspect ratio raised to the power of 0.68. This is for a straight tapered wing, minus 0.64 right. Using this expression we will be able to identify what is E, Oswald's efficiency factor for a straight tapered wing, and again it is based upon this empirical relationship. So, it is like 1.78 star, so 1 minus 0.045 times aspect ratio raised to the power of 0. minus 0. So, aspect ratio is a variable here. So, every time it will try to find out what is the new E. So, for a given aspect ratio, that means for a given j, this E value remains constant, right. That means, so it only varies. So, what we can do is, instead of doing this here, we can calculate it outside. Since it just depends upon the aspect ratio, what we can do is, this E is equals to, okay. So, this is just j comma 1, okay. So, what we can say is Oswald's efficiency factor, okay. So, once we know E, it is straightforward to calculate what is induced drag correction vector. So, which varies with E and aspect ratio. Again, this can be out of this inner loop, right. It does not depend upon wing loading. So, E K of I comma j, sorry, j comma 1 should be 1 upon pi E AR, okay. This is induced drag correction factor, induced drag correction factor or factor induced drag. So, CD CL by CD. So, CD naught I can estimate for this particular this thing, CD 0, or say directly CD naught of I comma j is equals to CD underscore design of I comma j minus K times K of j comma 1 times K CL underscore d square d of I comma j square. This is a profile drag and this is wing tip chord. So, drag coefficient at CL design. So, based upon, so this is 0 lift independent drag coefficient or 0 lift drag coefficient. That is zero lift drag coefficient, right, based on this parameters, that CL CD drag coefficient CL design and L by D, right. So, L by D is an input. So, CD naught is figured out. So, now I think it is end of the iteration, first iteration, and you can end the second iteration as well here. Okay. So, the outer loop is closed as well as the inner, sorry, not the second iteration, I am sorry. So, end of this inner loop and end of the outer loop. So, we can now plot what are how are these parameters varying with wing loading, right. So, let us say this is figure 1. So, subplot let it be what CL design, CD corresponding CD, and then say S, B, CT, CR, these are the planform parameters, right, for a given lambda. Here this is for a given lambda, we have iterated for different aspect ratio as well as wing loading here, right. So, that is what we have done here. So, let it be 5, 1, 1. Okay. So, plot, what I am going to plot is wing loading. So, this is small capital W underscore S, again this is in kg. So, I am sorry. So, this is WS. So, wing loading and how CL design is varying, right. So, wing loading will be more or less same for every colon comma 1 for every j, the wing loading variation will be same because we are varying it from 4 to 10 as I told you. So, the CD design so will varies with aspect ratio. So, let us say colon comma 1, this is for initial aspect ratio here, aspect ratio 4, we have 6 such plots here. So, we will try to star k and then we will hold on. I will just open our previous program. So, weight estimation program where we have similar figure that we have plotted just, oh, not in this, what was that? It was in climb performance, I guess. We have used hold on, right, for different plot. I do not think even this is going to help us. No? Okay. So, let us first save this. We are what are we doing now? Wing planform geometry. Okay, so we have this Control C, Control V. So this we are varying it to, let us say this is like plus. Oh, we can still have color code, right? Isn't it? So 3 and 4. So this is with red, this is with green. So how many? 1, 2, 3, 4 are done. 7 in total, right? From 7 to 10, it's like 7, isn't it? Sorry, 4 to 10. So this is like 5, 6, 7. Done with the first plot. So magenta and then black, blue, red, green, magenta, yellow. So there is no need to hold it on further, this particular subplot. So but by label what we can mention is design CL, C underscore L underscore D. The second plot, we want to vary, we want to see how the area is varying, right, isn't it? but CL design, it varies with wing loading, not with aspect ratio, is not it? Am I correct or not? So, it is like same W by S, it will not have the variation with aspect ratio, there is no point in doing this. Yeah, I am sorry, because this is not going to vary with aspect ratio, right. So, there is no need of holding it on, and the simple y label is, yeah. So, plot the second subplot, let us do it for say variation of S. In fact, S will also not vary with aspect ratio, it just depends upon wing loading, right. So, wing loading is independent of aspect ratio, here is another variable of this iterations. So, CL design and S are independent of aspect ratio, geometric parameters here. So, what I have is simple, no, if you plot any one of this, it will remain constant here, right. So, plot WS, there is no need for this entire story, otherwise I will just copy this so that I can use it for the other plots, the third one. So, what I am going to do is delete this and then simple S here, right, S in meter square, done. So, the third one will vary how the span is varying with B. So, B is varying with aspect ratio, B in meters. And with the input of lambda, we are able to find out what is root chord like CR and its variation with aspect ratio CR here, right. Okay. So, we are plotting CR variation with aspect ratio for like CR variation for W by S and cross plotting for and we are holding on the same plot and we are superimposing for various aspect ratios here, right, CR variation with various aspect ratios. And similarly, we can do it for CT. Here C underscore R in meters, there is capital R CR root chord and C underscore small t. So, it is done. So, the X label here is X label. If you just want to see how the drag coefficient is varying, then we can have another plot here. Just immediately after this, we can have another plot. Let us label it as 2, 3, 4. And CD is again, of course, it depends on L by D and yeah, it depends upon C design and design L by D for that particular design, right. So, it is independent of aspect ratio here. So, we are not considering that here anyway. So, and K is independent of this wing loading. So, CD naught again is like it can be outside, but CL design, yes, is independent of aspect ratio here, but K depends upon aspect ratio, it will not depend upon wing loading, but CL design depends upon wing loading, but not on aspect ratio here, right. So, we have added another plot in this subplot. This is more or less done, variation with CT, CR span and then CL design, CD design and then the wing area, how it is varying, right. So, with respect to wing loading, right, wing in kg per meter square. So, I am just using kg per meter square here. So, wing loading variation in kg upon meter square. Let us try to see if we can run this code. So, what is the altitude of flight? It is in meters, it is say 2000 meters. 30 meters per second, and weight of the UAV is 8.1 kg, taper ratio is 0.4. So, you can now see if you insert legend here, so insert legend, yeah, okay. So, black stands for aspect ratio 4 and it increases 4, 5, 6, 7, 8, 9, 10. So, this color cyan, this greenish blue, right, I call it that way. So, it corresponds to aspect ratio 10, right. So, if you look at this, the wing area when you are flying at, so this particular for these 3 parameters just depends upon wing loading here, right. So, it is, so the wing area turns out to be, so at wing loading 10 it requires about 0.8 meter square, right. So, when you are flying at a lesser wing loading for these mission requirements, you end up close to 2 meters per second here. 2 meter square, sorry, it is close to 2 meter square, and the CL design is, say, it is far less when you are flying at a lesser wing loading, is not it? It is about 0.08, it is not even 1, right, 0.1. So, and then when you are flying at higher W by S, right, is not it? So, higher wing loading, because the velocity is quite high here, that is the reason why. So, this is about 0.25, 0.22, right. So, the CD CL design, CL design, no, this is CD design, I am sorry, we need to correct it in the plot. So, the second one is CD design, right, CD for that CL design. So, I am not running it again here. So, this is about 0.115 when you are flying at WA by S of 10 kg per meter square. So, you can see the tip chord here is with the 0.4 aspect ratio, see how the variation of CT with respect to wing loading. So, the tip chord turns out to be about 16 centimeters, right, and the root chord turns out to be about 40 centimeters. So, 40 centimeters will be the root chord and tip chord is 16 centimeters, and the corresponding span of the UAV is about 2.8 meters. So, I am talking about wing loading of 10 here, right, 2.8 meters approximately. So, when you are planning to have a hand launch UAV, it should be at least W by S should be at least within 6, you should not go for higher W by S, because you need higher launch velocity then, right. So, say 6, the CT is about 20 centimeters or 21 centimeters close to, and then the CR is about, say, half a meter, half a meter of root chord, and the span is about 3.6 meters, 3.7 meter span for this particular UAV, which is weighing about 8.1 kg, right. So, the area here is about 1.35 meter square, and the drag that you may encounter is, so this is quite less here, 0.01 close to, right, and so the design CL is about 0.13. Okay. So, this is how we can complete the planform geometry selection. So, in the next lecture we will try to look at what is the cross sectional properties for this particular planform, what should be the cross sectional properties. Thank you.